Okay. Now she can X out. And we'll-
Okay. Just gotta be, yeah, that's what I was doing fast.
Yeah, that's just gotta be on. I think you want to somewhere up for her to get.
Yeah.
Oh, I see.
Yeah, I was been instructed on exactly where to flip it. It has to be symmetric so that when you turn your head from side to side, the volume doesn't go up and down in triples. So your kids are home? They didn't want to hear us guy talk?
Yeah.
Yeah,
Well, they.
my astronomy 191 students show up and take a nap. And it's it can be very restful. Just the high point of my professing career, I had the starting center of Tubby Smith's team that won the national championship. And he used to sit in that corner way over there, just as far as he could get. And he had two guards. So the guards were there to take notes and make sure nobody bothered the center. He slept the entire semester. And I remember when we got to the final four, they won the national championship. At one point, the score was tied. He got fouled and came to the free throw line, and he sank all the free throws. And my wife asked me, "Is that your astronomy student?" And I told her, "I think so, but I can't be sure. I've never seen him with his eyes open." But he sank all three, and I think that's because of 3 hours a week undisturbed sleep in the corner of his astronomy class. He was rested. He was rested and ready to go. Hmm? I forgot that. I forgot the guy's name. He was a nice guy, actually. He you would think of centers as being super duper tall. He wasn't. He was taller than me, really. Okay, welcome. I'm going to get started. It's 2 minutes early. I want to get started so we can get finished, so we can go across the street and have a look through the telescope. You probably came here to really see the cosmos. We're going to talk about the cosmos, but you can actually see the real deal as soon as we're done here. So welcome. This is the Kentucky Sky Talk. This is a series of talks we have the second Thursday of every month. As sort of a service component of the MacAdam Student Observatory. So if you've noticed, the top of the parking structure has a dome on top, and that's the MacAdam telescope. And so we in astronomy are very, very fortunate. The society has allowed a few people to spend their careers thinking about the heavens. And so we're very appreciative. Thank you very much. But we've discovered some wonderful things. We've asked some fantastic questions, particularly the questions we're going to ask today. And the purpose of these talks is let you know a little bit about what we found on our journey. Okay, so I'm Gary Ferland. I'm one of the astronomers here on the faculty, and this is the first Sky Talk of the fall semester, and so welcome. I'm going to start out with the biggest possible question of all. How was the universe born and where did it die? How will it die? And so these are questions at the very edge of what we as humans can ask about the universe around us, the birth and death of the universe. We know a lot. These are, if you think about it for a second, these are absurd questions. How can a human answer this? And a human can answer it by being very clever and thinking very hard. So people have been looking at the sky for thousands and thousands of years. And we've been living on the Earth for a very, very long time. So we look out at the cosmos. Here's the constellation Orion. There's one constellation everybody can recognize. You see this bad boy up there, and you just know that's got to be a constellation. And here's the Earth below us. Over a human lifetime, let's say you live 100 years and watch the world around you, it never changes. It doesn't change much. The seasons change, the weather changes. The constellations don't change, and the giant mountains and rocks don't change either. And so, what people instinctively knew for thousands of years is that the universe was just here. Now, this is a diagram. I'm going to show you another version of this diagram in a few minutes. But if you want to conceptualize how the universe is changing, up until about 1930, everybody, all the philosophers and scientists, has basically told you that the universe has always been here, more or less in the current shape, and it always will be here. And then that begs, you have no origins question, and you got no question about the fate and evolution of the universe. So the way this is drawn here is a timeline going up. And so the distant past is off the bottom. The present is where this yellow line is, and then the future is going higher up. And so what's drawn here is kind of the scale into black ovals. This is kind of the universe there. So it's keeping the same size. It's always the same. It's very comforting because you can trust this universe. It's not going anywhere. And then you don't have any deep philosophical questions like, where did it come from? How did it begin? How will it end? So if you look around us, you start to see structure in the universe. And this is our Milky Way galaxy. So this is a galaxy which is held together by gravity. Our solar system, our sun, and the Earth are captive as orbits inside the Milky Way. It takes us about 250 million years, about 250 million years, to go around the galaxy one time. And so the gravity holds the whole thing together. And we're going to find gravity playing this big increased role across the entire universe. And we're going to be thinking a lot about gravity. So gravity is what gives us our weight, pulling us down to the surface of the Earth. And it's an attractive force. The gravity we know about always attracts other things. There's no anti-gravity, but we'll get to that when we get to the parts we don't understand. So if you watch science fiction, I think in Star Trek even had it, there are anti-gravity devices and massive objects who just float there in the air. That doesn't exist. We can't do that. Gravity always pulls things together. This is our home galaxy, the Milky Way galaxy. Just as a show of hands, welcome, come on in. How many people have seen the Milky Way? Okay, it's a good crowd. Normally in the daytime astronomy, nobody raises their hands. I'm not sure, maybe it's something to be ashamed of, but I think the problem is if you live in cities, if you live indoors, you'll never be in an environment that's dark enough where you can actually see the Milky Way. You've got to get away from the city lights. On a moonless night, and you can see this band of light. The ancients called it the backbone of night. They thought the Milky Way, you see it as an arc across the sky. They thought it was the backbone holding up the sky above our heads. It's not, it's just a lot of stars held together by gravity. You go farther away, then you find what's called the local group. So we live in what's called a cluster of galaxies. We're not by ourselves. The Milky Way galaxy is not by ourselves. On this image, the thing with the spiral arms off there on the left, this guy over here is us. There's lots of satellite galaxies around us. If you go back to where we were here, you can see two of the bigger satellite galaxies. These are kind of moons going around the Milky Way galaxy, captured by our gravity. And there's a cluster of galaxies here, and we have another clump of galaxies about 10 million light years away, which is called the Andromeda galaxy. There's a lot of images of it. It's very prominent. It's almost our twin. So there's two galaxies that look like that, big galaxies, and lots of little galaxies. This is the local group, and the local group is held together by gravity. It's not doing it. It's not expanding. So I'm working way to the expanding universe. And so what's expanding? The sun isn't, the earth isn't, the Milky Way galaxy is not expanding. And this local group also is not expanding. By expanding, meaning moving apart. If you go to any scales bigger than this, to things more far away, it gets challenging. As things get far away, they get very faint. And it's hard to do precision measurements if you don't get much light. So that's why astronomers build the biggest possible telescopes to gather together the most light. If you go far enough away, you can make maps of the universe that look like this. Now, it's going to take a little bit of time to think about what we got here. So here's the Earth down here. And what they did on this map is they got a telescope. And they took a swath around the sky like that. It took years to do this. They would look across the sky, a swath across the sky, and then using the telescope, they would measure the distances to everything they could see in front of the telescope. So they could probe out farther and farther away from the Earth along this swath. And the way it's presented is sort of a pie cut or a pie wedge across the universe out to a billion light years away. What does that mean? A billion light years away. Well, none of us can conceive of a distance like that, but it's convenient in astronomy to think about the distance that light can travel in 1 year. And that's very far. The nearest star to us, about 4 light years away. The Andromeda galaxy, a couple million light years away. The light year is a great system of units because that tells you, without thinking any farther, what we call the look back time. So astronomy has a big disadvantage. We can't do an experiment, but we have it's not like physics. You stick a thermometer and figure out how hot it is. We can't do an experiment, but we have compensation. We have something nobody else has. We have a time machine. We can look back in time. And so if you look at something 10 light years away, the light was produced 10 years ago, and you would see it as it was 10 years ago. In this case, we're looking back a billion years into the past. And In comparison, the universe is about 14 billion years old. So we're looking at, a good way back into the past. And what you find, what they've got here drawn, is sort of weird colors, is the galaxies they detected. And you can see the galaxies aren't just spread all over the place. They form clusters of galaxies. It's kind of like our local group, and they make these big arcs. Fascinating problem in its own. But what I think about is something that astronomers can measure is how fast a galaxy is moving away from us. We use what's called the Doppler effect, which is exactly how the police give you speeding tickets, which you can use light that comes to you that you detect. And if you look at it very carefully, you can figure out the thing that emitted it. Is it moving towards you or away from you? And you can figure out to high precision how fast it's moving. So these lines that are drawn on this are an indication of how the universe is expanding away from us. So close to us, down here at the bottom, if you can see this mouse, the arrows are short. And so this might be only, say, 100 million light years away, 100 million years in the past. These galaxies are moving at lower speed, and then the more distant galaxies are moving faster and faster and faster. So that's what you get if you have an explosion, or some things that at one point in time, something blew up. Some things flew off very fast. The ones that flew off fast, they get far away. And the ones that did not go off very fast, they're pretty close in. So this is discovered by Edwin Hubble, a former basketball coach who's a native of Louisville. He actually was the captain of a Big Ten championship basketball team. University of Chicago was in the Big Ten at that time, and they won the Big Ten championship. So the guy who was the captain of that team, well, he also discovered the expansion of the universe and the age of the universe, which we call the Hubble time in astronomy. So this means the universe is expanding, and it looks like it's expanding away from the Earth. It's not. Everything is expanding. And that means something very, very deeply philosophical. So this happened about 1930. Before 1930, everybody would have told you the universe had been here for forever. And it's not an interesting question. But as soon as the Hubble expansion was published, we realized, well, that there was a beginning. And we got the beginning pinned down pretty well right now. It was 13.8 billion years ago. It's actually known to four significant figures. So we got that thing pinned down. There was a beginning. This changed everybody's view of the universe. It had a beginning. What can we find out using physics about that beginning? That's every bit. If you've been watching the news, there's very weak evidence that Mars had life that was announced by NASA yesterday, the day before. So if you knew for a fact there was other life in the universe, that would be every bit as big as discovering that the universe had a beginning. It wasn't always like this. So then you have that brings up two interesting questions. The expansion of the universe brings up two interesting questions. From measuring the expansion, we know that the universe had a beginning of about 13.8 billion years. We understand actually a good part of what happened from the very beginning up to now. Our physics that we understand, as we understand it, applies over what we've seen. They start looking into the future and some of the things right now. The physics as we understand it is not complete, but we can still see where things are headed. So it had a beginning, and then the question is really the topic of this is how will it end? It's kind of a downer. It's just going to keep going, and it's going to become cold and dark and dismal. But let's figure out why. Okay, so we saw these are four possible universes. The first one we saw was unchanging and just kept going, and everybody without exception knew that's how it worked until 1930. So the universe is expanding. So that's where we are with Edwin Hubble. So here's starting with a big bang. I'm not going to go into the big bang today. We're going towards the future. So on these diagrams, the big bang is just like a little firecracker. The big bang is bigger than that. But so something went off in the past. So this is a timeline going on. This is in the past. And something and the universe started expanding. So that's what these ellipses are trying to show, that the universe is expanding and getting bigger. So it's only over the biggest scales, the clusters of galaxies are moving apart. Our galaxy is not expanding. If you mind your diet, you're not expanding too. There's the famous freshman 15. The freshmen expand by 15 pounds when they first come to UK. So anyway, there's several possibilities. The universe is held together by gravity. I'm not going to try to do this, but if you take something, throw it up, Earth's gravity will pull it back down. So I threw it up at the Big Bang, gravity pulled it back down. So one possibility is that the universe will start expanding. Gravity is trying to pull the whole works back together again, because gravity only knows how to do one thing. It pulls things together. There's no antidote. Okay. And so one possibility is that gravity will win, just like when I threw this up, gravity won. It flew up a bit, then it came back down. So that's the universe that was started out, right? So we're in the expansion phase. We can observe that. We're in the expansion phase. And if gravity can win, it'll pull it back together again. And then you would have something that you call the big crunch, when the Big Bang goes back together again. And then, interestingly, philosophically, you could get around the origins problem by saying, well, maybe the universe bounces. It comes back it goes up, this big pulls back together again, big crunch, and then it bounces back and have another Big Bang. That would be an oscillating universe. But these are both accelerating universes. The next one is it expands, and if the gravity is just right, it will expand until it stops expanding, and it's huge. Another possibility is labeled here as a coasting universe, where the gravity has no effect, so it doesn't start pulling it back together. So it expands and expands and expands, and gravity never pulls it back together. And then there's an accelerating universe, where the expansion starts, and then something pushes the universe far apart. Now I've got a precision measuring instrument right here. I want to take a vote of the honest citizens that have come out to our Sky Talk. So I have a meter up here, and it's acoustically tuned to this room. So let's have just a clap. Let's have a round of applause just to calibrate the meter. Wake up, clap. Okay. Now we're going to take a census. How many think we live in a decelerating universe that'll get big, get pulled back together, bounce, and maybe come back again? Clap if you like that one. You have to clap too if you like it. Okay. How about decelerating, where it goes big and then this never comes back? Okay. How about a coasting universe? Like this. Okay. And how about an accelerating universe? Okay, so I don't need to give this talk. That's what we have on our hands. There's a mysterious force we don't properly understand that's causing the expansion to continue. It's called the accelerating universe. So careful measurements show that the expansion is speeding up. And so it will never collapse in on itself, as near as we can tell. It's an accelerating universe. It's being pushed apart by something. It's called dark energy. But a way to think of dark energy, the way it works, it's very mathematical in the equations of general relativity. The way to think of dark energy is behaving like anti-gravity, where things are repelling each other. This dark energy anti-gravity was not important in our past. It's only becoming important around now. And the way the observations show, it'll probably become more important in the future. So this is a somewhat gloomy conclusion. The universe will expand forever and last forever if the laws of physics as we know it right now, are true. I want to get an interesting side. Welcome, come on in. So we orbited around the sun. 150 years ago, people were very interested in understanding how the sun works. They can do it because stars are super simple. The reason for that is they're amazingly hot. So there's nothing complicated in a star. There's no molecules deep in a star. There's no rocks. There's no buildings. There's no I-beams deep in a star. It's so hot that a star is vaporized all the way through as a gas. If you had a starship or a spaceship that could take the heat, you could dive it. This is our sun, straight into the sun. If you fell into the sun 2 weeks later, you would pop out the other side, having hit nothing solid at all. So the mathematics of treating this is very, very simple. The way the sun works is that gravity is pulling things together. If you were to stand in the sun, you'd weigh hundreds and hundreds of pounds, way more than you would stand here. Gravity of the sun is what holds our solar system together, it holds the Earth going around the sun. If you turned off the sun's gravity, the Earth would go off in a straight line at 50,000 miles an hour. And within a few days, we'd be so far from the sun that it'd get very, very cold. It's the sun's gravity that holds us together. It doesn't become a black hole. If you only have gravity pulling together, you got a black hole in your hands. There's gas pressure holding it up. So there has to be a source of heat in the very center of the sun, generating the pressure that holds it up. So this diagram shows that there's two forces together. Gravity is pulling things in, like this blue line, the blue arrows here, and then gas pressure is pushing it back out. They had figured this out by 1880. They understood this and they got the right answer. If you look at what they had done in the 1880s, they got the right answer. They had figured out the conditions in the center of the sun. The problem was they didn't know about nuclear physics yet. They had enough physics they could do, but they didn't know about nuclear physics. And this heat and pressure in the sun is caused by nuclear reactions. It's a nuclear reactor, a nuclear power station. And so they knew how to figure out how long the heat would last, as something called the Kelvin-Helmholtz contraction. And the sun would only last tens of millions of years. But so that means the Earth could only, with life, could only be tens of millions of years old. But at that time, geologists, by looking at conditions of salt in seawater, they knew that the Earth had to be 1 or 2 billion years old. We know now that the Earth is 4.5 billion years old. There was a puzzle. They couldn't figure out what was holding the heat of the sun going for 40 years. It was in 1920 that people first put together the idea of nuclear energy generation. But there's a good 40 years that they had a puzzle that's a lot like the puzzle we're going to get to next. They could see the sun had to have an energy source. There was no known energy source, so the sun should have cooled off. We come across two puzzles when we start looking at the universe at very, very large scale. So there's clearly two parts of physics. They're probably unrelated, but it's a guess, but we don't know what the answer will be. The first is what's called dark matter. I said very glibly that the Milky Way galaxy is held together by gravity. We measure that very precisely. The local group of galaxies is held together by gravity. The problem, though, is you count up all the stars. You can do that with a telescope. You count up all the stars that are out there, and we know how much mass a star has. There isn't nearly enough mass in stars to account for holding together the Milky Way or the local group. In fact, about a factor of 5. It's not a small problem. So it has to be 5 times more matter holding the galaxy and the local group together than we can see in stars. So it's not stars, so it's given the name dark matter. That has to be correct. It's matter in some form that's making gravity that doesn't make any light. We don't know what it is. We don't know, you can say we have no firm evidence what it is, but there are lots of ideas. There's a part of physics that studies the nucleus and what are called elementary particles like electrons and protons and neutrons. And people in that part of physics have ideas of how there could be a different kind of particles, kind of like protons and neutrons, electrons, but not exactly the same. But they would have mass, but these particles would not interact with light. So they would not be possible to make light. We have not detected such matter. There's a lot of people are working on it in our very department. It's called particle physics. And it's one of the grand challenges, try to identify what the dark matter is. So people are attacking it from theory by working with equations. And there are also very, very large experiments being built to try to measure what happens to matter in extremes. So this is the first of the big puzzles when you start looking at the universe at large scale. Nonetheless, we see that gravity works exactly as we suspect it should. We can't see what's causing the gravity. So seeing the gravity, you do that with a telescope. It's empirical. What we're getting to is what's causing this acceleration, this outward acceleration, this dark energy. And if you do a consensus of the whole universe, I shouldn't say this. This is really airing out our dirty laundry. You're going to get up and demand your money back. But the part we really understand is this part in yellow. These are the electrons and the atoms, carbon monoxide, things that we have understood for almost 100 years. The dark matter, which you need, we can't detect it, but we need to hold together the galaxies as a quarter of the total. And then this accelerated expansion we'll talk about next. That's actually the majority, almost 70%. So you stand before you saying, stick with the talk, but we really do understand 4.9% of what's out there. But there's a lot of educated, it's not an educated guess, we can measure what the others are doing. These are direct measurements with very, very large telescopes. So let's shift gears now and think about what is the long-term evolution of the universe 1 trillion years from now? Well, we can answer that. This is the evolution of the Earth in our solar system. The Earth is about 4.5 billion years ago. Today on this scale is right at this zero right there. So on the left, we're going backwards in time. And you go back, we know the birth of the solar system is 4.5 billion years ago because the meteorites, these stones that fall from the sky, date back to that time, and they fall on the Earth, make shooting stars as they're coming down. Some land on the Earth. You can take them to the laboratory, and you can measure how old these rocks are. And so they date back to the birth of the solar system. On this scale, there's been life here on the Earth of one kind or another almost from the beginning. The oldest life, it's a little bit controversial, 3.7 to 3.9 billion years ago. There was very, very simple life. This would be very simple life you'd need a microscope to see, not bunny rabbits, anything like that. The big growing things like us or the dog have only been around in one form or another on this red area this last 500 million years. So it's only a small part of the history of the universe. So here we are on our planet. The planet has been sort of like this for hundreds of millions of years. It will continue to be sort of like this for another few 100 million years. The problem is that in stars like the sun is burning up its fuel. It's changing hydrogen into helium to make nuclear power to generate the heat that can hold it up. So it's about halfway through its life, it's burned about half of its fuel. So the engine in the sun is running short of fuel and it has to work harder. It sounds crazy. You think if you're running out of fuel, you'd burn it more slowly. But the way stars don't think that way. When they start running out of fuel, they get big and bright. They get very, very bright. And our sun is now brighter than it was in the past and is still becoming brighter still. Over 100 million years, you don't notice the change. It's very, very slow, but we have very complete models, computer models of how the sun works inside. And if looking into the future, it's going to become hotter and hotter here on the Earth. Mars will be comfortable. Right now, Mars is very cold. In a couple of billion years, you can move out to Mars. It'll be comfortable out there. The Earth will be very, very challenging to live on the Earth in a couple of billion years from now. It'll be too hot. The oceans will eventually boil a little over 3 billion years from now. And then the sun will keep getting hotter and hotter and hotter until nearly 8 billion, after 8 billion years from now, the sun will throw off its outer layers and die. So the way stars die is they're very generous to the galaxy. It doesn't just die and go into its grave. It throws off more than half of its body. The body of the star is thrown off into space, the space between the stars, and is recycled to make new stars. And so the atoms in our body, we've known is in the Bible. We came from the earth, we'll go back to the earth. The atoms in our body is from food that we ate, and in some cases, food that your mother ate when she carried you. And so we know the atoms in our body came from the earth, and the atoms in our body have been through this process. The earth is only 4.5 billion years old. The universe is nearly 14 billion years old. So there's plenty of time for other stars to have been born first before we came along. There's a very complete theory of how stars work and how the galaxy changes. When our sun dies, it will throw off the outer half of its material to the galaxy, and then new stars will form from that material using the leftovers from our solar system to make a new solar system. A different sky talk, but it is very, very strong evidence. The atoms in our bodies have been through this process about 2 or 3 times. But it is from the birth of the universe to the formation of our solar system is almost 8 billion years. That's a lot of time for things to happen. So the sun will die, sunset on the sun. The sun will die. It won't just simply fade away. It will throw away the outer half of its body. The rest of it will become a dead star with no power. In the case of our sun, it'll become something called a white dwarf. But these stars are dead. They have no energy source. And looking into the far future, it will just fade away, become darker and darker and darker. But the material thrown out into the galaxy can be used to recycle. There's a big recycling program going on in the galaxy. And so what we've been talking about is the sun. That's the upper right here. When the sun ages out and dies, it will throw off this outer layer. So it will become very, very big and distended. The earth will become a barren rock. When the sun actually does die, when the star actually does die, it throws off its outer layers in one of these 2 ways. Our sun will die in a very gentle death like this, something called a planetary nebula. That's something I used to work on when I was much younger. And so they're beautiful to look at in the sky. Much bigger stars have far more interesting lives than the sun. They can explode very, very dramatically. This is something called the Crab Nebula. When it exploded about 1,000 years ago, it was so bright you could see it in daylight, and it was visible for several months. And there's something called a neutron star left inside there. This material that's being thrown off has been affected by the nuclear reactions of the star when they made energy, and that builds up the elements from made of. It's thrown back out into the galaxy. This is a kind of a binocular level view of a nighttime sky. So this is a big piece of the sky, lots of stars. But you can see that there's something blocking out our view of the stars in this direction. So it's not a black hole at all. What this is what we call an interstellar cloud. It's a very, very large clump of gases between the stars. You know, the stars, these are stars. So this is really big. The distances between stars are there. So these are gases that have been thrown off from dying stars, and gravity will pull these gases together again. So you go back to the beginning of the cycle, the upper left. So here's these gases here, they're being pulled together by gravity, and then that forms a disk, good property of another sky talk. And then in the center of this, the sun forms, and the cycle continues. So it's a cycle, and it's in the case of the atoms around us, we've been through this cycle 2 or 3 times, probably closer to 3. The problem with this cycle is it's not 100% recycling. Every time you go through this cycle, some of the dying stars that throw out the outer material leave behind black holes. So a black hole is a lost cause. You're never going to dig the material out of a black hole. And if you have a black hole out in space, it's just black. It doesn't make any light. The sun will create a white dwarf, which has no energy source. It will take a long time, but the white dwarf will cool off and become cold and dark. The Crab Nebula made a neutron star, which is also cold, is also dead. So as this process goes on, every time you go through this loop, some of the material is lost forever. It goes into one of these dead stars. So you end up with a bunch of black holes. You got to wait a while. It might take 1 trillion years, but this is the eventual fate. Once you end up in a black hole, there's no way to get back out. There's nothing you can do. And it's been a lot, there's an experiment called LIGO, which is actually measuring what happens when you take 2 black holes and let them collide with each other. So a lot happens, nothing we can see because they're black holes, and they coalesce and make a new black hole. So they just get bigger and bigger. So this is lost cause. So looking into the far future, next couple of billion years, the sun's going to be here, the Earth's going to be here, the sun's going to be a star. The problem is the sun's getting brighter. It's not getting hotter and brighter, it's getting colder and brighter. Crazy, but that's what it's doing. We understand the sun. The sun, understanding the sun was Nobel Prizes 60, 70 years ago. We've understood this for a long time. Looking for finding something to be optimistic about. You want to buy real estate, go out to Mars. In a couple of billion years from now, Mars will be comfortable. Right now, it's horribly cold. 7 billion years ago, the sun will go bye-bye. It will become one of these dead stars, and it will shed off. It will recycle its outer layers for future generations to use. The cycle goes on and on and on. Every time you go through the cycle of star birth, star life, star death, recycle, star birth, you end up losing material to the black holes. And it's estimated to be about 1 trillion years. Now, how can you imagine 1 trillion years? Star formation will stop because material will have ended up in black holes. If the universe keeps going on and on and on, this is what has to happen. About 100 trillion years from now, the very lowest mass stars, this is a paradox. Most of the stars in the sky you see are dying stars. They're very bright stars at the end of their lives. The really big, bright stars like Rigel or Betelgeuse in the constellation Orion, those have masses 50 times the mass of the sun, but they live a very short time, only tens of millions of years. It's the little tiny stars. They don't have much fuel, but they don't burn very brightly. They can last 1 trillion years, the smallest stars in the galaxy. So after a couple 100 trillion years, the last stars will gone, the universe will become cold and dark. This is kind of the limit of where what we understand about physics is known. We don't know for sure, for instance, is a proton stable, is an electron stable. Uh, over this kind of time, there's a lot of question marks. And so you can make educated guesses about what will happen out to about 1 trillion years from now. The takeaway is that it's really, really easy to do a very, very high definition 3D image of what the universe will look like trillions of years from now. And here it is. Thank you very much. Okay, so what I propose, Erica, you did this. You want to do the honors? Or someone's going to do the honors. We have a door prize.
Uh, crash. That's
There you go.
All right. You what? I see. Down there, approximately 3, 4, 5 times. You 6, 7, and number 8. Yeah.
How are you going to do this? Oh, you're first.
Drum roll first. Got all right. You're the 1 minute time.
So that is Copernicus. That's what it's a crater you can see with a pair of binoculars on the moon. The last Apollo flight, what would have been Apollo 20, was going to go to Copernicus. It was canceled. And they were going to had a rover, they were going to drive to that mountain you see in the center. So it's very, very prominent. It's a very young crater, about 100 million years old. And it's very big as well. So it's a great crater. So what I propose doing is, if you have questions, 1 or 2 questions, we have a little bit of time, 1 or 2 quick questions. I'll stick around if you want to talk about things. Of course, the excitement is to go see the telescope and see this universe we've just been talking about. No questions?
So, from our telescopes, by looking at the light objects, we can tell things are from the way and farther things are moving more faster. But I guess just not really. It tells that the space itself between matter is standard. Probably it could be the case that we have this massive amount of space.
That gets into general relativity, which is the theory of space and time. So, but an easier way to think of it is just you set off a firecracker and the pieces are flying out. Space-time, in general relativity, space is expanding. So if you, but you don't need to go that far. It's hard to visualize because it's 4-dimensional. It's hard to visualize a 4-dimensional space. It sounds like a cop out. The clean way, the way it most often is described in older textbooks when people were home baking a lot, is you take a loaf of raisin bread and put it in the oven, and the raisin bread would expand, and then the distance between the raisins would get bigger, and every single raisin would see a Hubble expansion. Now, I've never baked raisin bread in my life. I wonder who has. But this was the classic explanation soon after Hubble described the expansion. And so now it's most often just described as an explosion. It's called the Big Bang.
for theoretical reasons, we must reasons of general relativity.
It's described by general relativity. In fact, Einstein, there's less of this in meet the eye. When he did general relativity was done over about 5 years in the late 1910s. And when he first did it, everybody knew that the universe was just standing still. And it lasted forever because Hubble hadn't discovered the expansion yet. So Einstein's equations said there are two things you can do. You can go up and you can come down. It's gravity, like that. So what he had to do was he wanted to make a universe that was just hovering there. He had to add something called a cosmological constant to change the equations of general relativity so the universe would just be sitting out there in space. So they knew about this, and Einstein was trying to get a static universe. If he had the courage of his convictions, Einstein could have predicted the expansion 12 years before Hubble discovered it. But he backed off and he fiddled with his equations, so he ended up with a universe which is standing here. Okay, so the plan is Erica. We have the GAs here. So there's 3. So it's a body team of 3. The observatory is on top of that parking structure. You go to the very top. And so there's an elevator, or you can climb the stairs. Anything else to add?
Yeah, you guys are give it that and bring it out. We'll have to hang out. We'll finish before you start to see anything, but yeah, it's a lot of people actually travel about and all of so we'll shut down here and then any interested in coming hang out in the hall here. Grab people.
Thank you.
And looks like had 12 people on YouTube. But yeah, I totally missed that. I don't think all this is awesome. That's totally